Hello. All right, so we're going to build off our introduction of magnetic fields, and we're going to start to now kind of trying to better understand some of their properties. And we're going to look at some results and applications, particularly when we are using a uniform magnetic field, where the magnetic field is the same everywhere. Well, let me review briefly some of the stuff that we walked away with from the last video, and elaborate on some of the things that I realized I did not state perhaps at all or as clearly as I could have in the previous video. So right here we have reviews and some elaborations. The first thing we started talking about is the simple permanent bar magnet, that had some sort of magnetic field that seemed to that has a dipole-like nature. We call this a magnetic dipole, where it has this north end and the south end. The north end and the south end are defined as, when we draw this magnetic field and associate this direction with it, that the side of the magnet where the magnetic field comes out, we call the north end. The side where the magnetic field goes back in, we call it the south end. Now, what I did not comment on is that this dipole is what appears to be, experimentally, the most fundamental building block of magnetism. Unlike electric charge, where you can even subdivide things even further. So let's think about with electric charges. Here I have a positive charge and a negative charge, and that forms an electric field coming out of positive charges and going towards negative charges. And this was an electric dipole, where it has a positive charge and a negative charge. Of course, I could subdivide the dipole even further. I could take the dipole apart and look at just this positive charge or just this negative charge. And I can have objects that are monocharges, right? They have either only a positive charge or only a negative charge. And even if this is, say, a proton, I could take the proton and I could cut it open and take out these things called quarks, and they have fractions of positive and negative charges. Nonetheless, the takeaway being is that for electric charges, though, I can get down to this, the individual Lego blocks that form, electricity can be monocharges, individual single charges. And my door is open, so what's that? This seems to be different in magnetism. Unlike electricity, it seems that with magnetic, I don't want to say magnetic charges, but with magnetic, pieces, what is the smallest block for magnetism? Seems that the magnetic dipole is as small as you can go. You can never get just a north pole, or you can never get just a south pole. And you probably have talked about this, in some previous course, where if I take a magnet and if I were to chop it into pieces, one of those pieces would then become itself its own small little magnet, which would have a north end and a south end. If I were to take that and subdivide it even further, it would have a north end and a south end. And I keep going, and it seems like I never can ever get just a north by itself or a south by itself. Magnetic dipoles appear to be the smallest building block for magnetism. And that magnetism, the magnetic field, always has some sort of dipole contribution to it. So another way of saying this is that magnetic fields have no sinks or sources. Or again, for electricity, and this was important when we were formulating Gauss's law, that when we have a positive charge, that's kind of a source of electric fields. Electric field lines come out of the positive charge. And my screen has vanished. And then similarly for negative charges, you can think of it kind of as sinks, where electric field lines go into and disappear. You don't get that for magnetic fields. For magnetic fields, can't see where I can resize, there it is. For magnetic fields, they always form loops. So take the bar magnet, for example. If we were to look inside of this magnet, we would not see that right here is where the magnetic field starts and then it ends here. But instead, we would see that the magnetic field, once it loops around, goes through the magnet and then connects. And so there's this loop on this side. Then there's a loop that forms this one on this side. That all those magnetic fields are all just loops, connected loops. There's no source or sink like there is for electricity. And this is, based on experimental evidence. There is no experimental evidence so far that there are what are called magnetic monopoles. Sinks or sources we could call monopoles or monocharges for electricity. There seems to be no magnetic monopoles. Right? I can't get north or south by itself. There's some ideas that if these things did exist, maybe they existed in the very early universe when the universe was a microsecond old, shortly after the Big Bang. But it's very unclear. And again, there's no experimental evidence that there are any that you can have magnetic monopoles. We then built on how to describe the magnetic force quantitatively. So we stated that the magnetic field, which we have not talked about where the magnetic field comes from. We haven't considered sources of magnetic fields. We'll do that in the next lecture. But we did consider that the magnetic field acts on moving charges. So the magnetic field, if it's going to act on something, it acts on a charge, so there's some Q, and it has to be moving. There's some velocity. And we made some argument, some sort of experimentally, supported argument that the magnetic force takes this form. That the magnetic force acting on a particle is the cross product of the particle's velocity and the magnetic field vector, and then you multiply it by the charge. That vector uses the cross product, and for really quick review of the cross product, the direction is given by the right-hand rule, where I start with my fingers pointing along the direction of the first vector, and I twist my fingers so that they are then pointing in the direction of the second vector. My thumb, as a result, then points in the direction of the cross product. There are other ways to do it, like some people do this, and I saw one called like the flat hand rule, but yeah. I like or at least it's simpler for me, fewer things for me to remember. Because the thing with this one is that I can draw it so that all three fingers are perpendicular, but I don't need V and B to be perpendicular for this to work, right? I can have, like in this drawing here, I have V kind of going off in this direction, B is going off in this direction. There's some angle between them. It's not 90 degrees, but again, as long as I start with my fingers pointing along V, I curl my fingers to point along B, my thumb is pointing in the direction of their cross product, which is perpendicular to both V and B. This force is perpendicular to both vectors in the cross product. The magnitude of the cross product is given by something that looks kind of like the dot product, but instead of a cosine, it's sine. So, things we explored in class and for some of the class problems, we found that this force is maximized when V is perpendicular to B. Then, in terms of what's going to give me the biggest number here? Well, notice that nothing changes the absolute values. The only thing I really have control over is the angle between them. So if we're given Q, V, and B, if they form a 90-degree angle, my cross product is maximized. The cross product is 0 if they're parallel or anti-parallel, which you might be able to think of as a test, of whether something is parallel or anti-parallel. Just like how the dot product, if it's 0, tells you that they are perpendicular. So, yeah, and just to elaborate a little bit more mathy on this stuff. Again, the sign of Q does matter. So again, when I did V cross B and said that the force vector points up like this, yes, that's what my right-hand rule said, but I'm also assuming that Q is positive in that case. If Q is negative, I would just do the right-hand rule, and then I just have to remember to flip the direction at the end of the day. V and B, when you think of what is F perpendicular to, F ends up being perpendicular to the plane that is defined by the two vectors V and B. I think it's Calc 3, you learn what the equations for a plane are and stuff like that. And you'll see that if I define two vectors that are not parallel or anti-parallel, that well defines a plane that they exist within. And then this cross product gives you a vector that points perpendicular to that plane. In the context of Calc 3, you'll use the cross product as a way of defining the normal vector, which we have already talked about in other contexts. A way of creating the vector that is perpendicular to a surface. Okay, now let's get into some new stuff. So, I would like to do two new things that don't depend on whether or not B is uniform or not. So these are general results. I'll move that down and move it up when I need it. So some new results. First I want to talk about the work that a magnetic field does. And again, I don't need necessarily a uniform field for these results. So the first result I want to talk about is that the magnetic field does no work when it acts on an external charge that's moving at some velocity v. So I ultimately want to show that the work done by the magnetic field, assuming that, let me actually put, let's make this very clear, the work done by the magnetic field, so I'm going to write F sub B, the magnetic force, is 0. Now let's think about when do things do work, from the potential lecture. Speeding up and slowing down, the work energy theorem, work changes your kinetic energy. And remember that involves the dot product, right? It's thinking about the component of the force that is parallel or anti-parallel to the direction you're moving. By the construction of this force, right, knowing that the force is perpendicular to your velocity, that's the key. Your velocity dictates the direction you're moving. But if this force is perpendicular to it, how can it be speeding up and slowing you down? Of course, we can write this out more explicitly. So, what I will do is I will consider, I have some object Q, and it's going to go some small distance. This distance here is going to go some tiny distance, some infinitesimal distance, dr. And what is dr? Well, by the definition of velocity, that is just the same thing as the velocity times dt. In some small amount of time, where I can approximate my velocity as a constant, that one tiny calculus step I take is velocity times dt. So then a small amount of work then is going to equal the magnetic force that's acting on you at that time times dotted with this vector dr. And this is a vector. I should write this as an arrow. There we go. So, and then, of course, once I can write this down for every individual step, I then integrate the entire thing. But we don't need to do that because I'm about to show that this itself is 0. So, again, remember this is pulling out the part that is parallel to v, in a sense. Because it's pulling out the component that's parallel to the direction you're moving. Right, we can even make that more explicit here, where if I write F sub B, and then it's actually dotted with V, and then this entire thing is just multiplied by dt. So let me actually move that over here. I think it's more clear, more obvious. Now conceptually, of course, I can just say that this is 0. But if we wanted to write it out more explicitly, as you might in upper level E&M, I think we have enough sophistication that we can do that. So let me write out the formula for the magnetic force. V cross B. And this entire thing is dotted with V dt. Not sure why I put those brackets there. So in this case, we can look at this and ask, and again, just by the nature of the dot product, if this we know is perpendicular to V, and then the dot product says, give me the component that is parallel to V, well then of course this has to be 0. Doesn't matter what dt is or q is, we know that, or really the direction of B, or the magnitude, right? This is very, very general, a very, very general result. So as a result, then if I were to integrate that, that just says that the total work done is 0. At least in these kind of non-quantum realms. I think you can get the magnetic field to do work when you're dealing with spins, but in our case, the magnetic field does no work. So what does that tell us? Thinking back to the work energy theorem, work tells you about how you can speed up or slow down. So if you're doing no work, then what this says is that the magnetic field changes direction, changes the direction of the particle. And I can be even more explicit, actually. It changes the direction of the velocity vector. Changes the direction of v. But does not speed up or slow down. Does not cause the particle to speed up or slow down. Again, you can think of this as it changes the direction of the velocity vector, but it does not change the magnitude of the velocity vector. So that's a good result. Maybe we'll create a set of highlights that for this lecture. So let's see. Right, B does no work. B only changes direction of B. We can actually now be a little bit more explicit on what actually component of the velocity vector is being changed. So here we have our kind of the second result I want to work out real quick. That the magnetic force only involves and changes. Now we've just stated that it changes the direction of the velocity vector, but really what it's doing, now we can bring in B. We can bring in the magnetic field and think about when you create a force that's perpendicular to both V and B, it's only changing the component of the velocity vector that is perpendicular to the magnetic field. So I can write, if I write V perp, where that is the component of V that itself is perpendicular to B, that component is what gets changed in direction and not magnitude. The component of V that is parallel to the magnetic field never changes at all. And let me draw some pictures related to this. So, and at the end of the page. So let me now add some drawings to this. So let's have a velocity vector that is initially pointing up. Let's have a velocity vector that goes up. And then I'm going to have a magnetic field that's going to point out of the page. Remember, the circle with a dot means out of page. And we're going to take this acting on a positive charge, because I can always change the sign if I want to, but let's make our life simple. So in that case, if I point my fingers up along V and then curl them to point towards B, I'm reflected in the screen, but to me, my thumb is pointing to the right. So then the force vector for the magnetic field points to the right. And since V and B are at 90 degrees from one another, the magnitude in this case is, of course, maximized. But in this case, then, the velocity is also perpendicular to B. The entire velocity vector is perpendicular to B. And as a result, if we think of force, which of course is then the same thing as acceleration divided by mass for this particle, acceleration tells you how the velocity vector changes. This is going to cause the velocity vector to, if it's initially going up, again, I'm sorry if it's flipped in the screen, right, eventually it will start curving to the right on this piece of paper. In this case, the entire velocity vector is changing. The other extreme, of course, is if the velocity vector is parallel. So if the velocity vector is also parallel to the magnetic field, then there is no force, of course. Force, of course. But now let's take an example where there's some combination of both. And of course, putting the magnetic field out of the page makes it hard for me to be able to draw that. So I'm going to go to a 3D picture here. So here's the x direction, y direction, z direction. And I'm going to have the magnetic field point along the z direction. And then I'm going to have the velocity vector exist in this xz plane. So there's some component that goes along the x direction, and there is some component that is going along the z direction as a result. So there is a parallel component here, and then there is a perpendicular component here. As they start, right, again, I did not assume that the velocity and the magnetic field were started perpendicular to each other. In this case, they're not. It kind of looks like they're at maybe like a 45 degree angle with one another. Right, that angle being, you know, whatever this is. But in this case, and so you can imagine, I could write this velocity vector as a sum of two vectors. One that is just along the x direction, you know, using the example in the drawing, and one that is just along the z direction, using the example in the drawing. Notice that then I could ask myself, I could apply or evaluate the force on Q V cross B and by our definition above, I could replace this with V perp, B parallel, cross B. Then, I didn't state this last time, but again, you can work this out, and when you do cross products, in Calc 3 particularly, that the cross product distributes over addition and subtraction. So then this becomes Q V perp cross B plus Q V parallel cross B. And then we can think, well, if this parallel and perpendicular are to the magnetic field, then we know that the angle between these two vectors is 90 degrees. We know that the angle between these two vectors is 0 degrees. The second one, of course, gets killed because the sign of 0 is 0. So then this becomes Q perpendicular cross B. So, in evaluating the force, the direction is, of course, always given by the right-hand rule. Nothing has changed. Don't think that I'm changing the rules now. The magnitude is still given by QV B sine theta, where that's the entire V. So again, nothing has changed from before. What I've said here is that I've evaluated that really what's happening is we're plucking out the perpendicular component to V and using that to evaluate the magnitude of the force. And perhaps that's not too surprising, because when we talked about the magnitude of the magnetic force, again, I have not changed anything here. It is still just this, where I use the entire original vector V. But then you might see, aha, V sine theta. V cosine theta, we talked about how that's the parallel component. V sine theta, this is just Q B, and this would be V perpendicular in that case. So what this implies is that the perpendicular component is what gets changed. So going back up to this 3D drawing, I'll use blue. Right, this part here, that it is that vector there that changes in direction, never magnitude, right? But it does change the direction. This component here remains unchanged. Both in direction and in magnitude. because the magnetic field does not affect that component. The result of this is that when you have a charge moving through a magnetic field, it tends to follow a helical path as a result. Oh, look at that. I even have it written down. Let's see. Let's move some of this stuff out of the way. What we're about to do next. So, what we have here is that the uniform in a uniform magnetic field. Here now I am going to assume that's a uniform magnetic field just to make the picture a little simpler. A charged particle whose velocity has both components parallel and perpendicular to the magnetic field follows a helical path as a result. So, here's the idea. And let me redraw our main result from before, and maybe I'll make it so that everything's in the 2D plane. So if this is the magnetic field, and I have some velocity vector v, then there is a component v parallel, and there is a component v perpendicular. The perpendicular component changes, and only in direction. So again, if I think of if I think of v cross b, the force points out of the page. Note that if I do v perpendicular cross b, I get the same direction, and you must. Then in that case, it seems like the force points out of the page. The velocity is going to want to start to veer out of the page. Then you can imagine when it's pointing out of the page, v cross b, the force then is to the left, and then the direction is going to want to start to veer to the left. V cross b points now into the page. The thing starts to spin in a circle as a result. We'll work that out again for a synchrotron in a little bit. So one of the components remains unchanged, one of them does not. So if I have a uniform magnetic field, so here's B, and it's just a bunch of field lines where their density says something about the magnitude, but I'm just going to draw a bunch of field lines. And then I have a charged particle, again we'll assume positive, that's moving in with some velocity v. What happens is that once it gets into the region of the magnetic field, kind of a way you might picture this is that the charges kind of get locked to the field lines. So it ends up kind of doing something like, my hand is really shaky today, something like that, or it kind of ends up helically looping around a magnetic. You can think of it kind of as looping around a magnetic field line. And the size of the loop we're about to calculate. So in this case, what we're seeing here is that there's this general motion upward. Well, that's the v parallel component. That's never changing, right? So what that component then just turns into vertical motion for this charge as it moves through the magnetic field. And then the spinning part, you have the perpendicular component, but then that part is by the magnetic force ends up just spinning around, creating this kind of loop structure. So it becomes a helix, or a helical path rather. And you can talk about things that, if you want to be super quantitative about this, there's this thing called the pitch. So if I look at, say, from here to here, that's when the charge completes one loop, right? The pitch P is the distance. It's the distance traveled by the charge, essentially in one loop or in one period. It's the distance traveled. Parallel to B, parallel, anti-parallel to B in one loop. or 1 period t. So again, we're about to talk about synchrotron motion, where we'll be able to calculate things like what is the radius of this loop and how long does it take the charge to complete one of those loops. But again, never speeding up or slowing down, only change direction. Okay, so now let's talk about an important application, which is synchrotron motion. So I already drew some of this out, so let me bring it up. All right, so here's where we can use as our starting point. I'm probably gonna need more room, so I'm gonna move this down to other topics to cover. All right, so important application. And here we're now going to assume that the magnetic field is a constant. So in this case, I have this region over here demonstrated by this box where the magnetic field is uniform and is always pointing out of the page. So we're going to now try to analyze what goes on in this region when I have some charge that has mass m and charge q, which again I'll take to be positive, enters this region initially with some speed v0 that is upwards. So its velocity vector is entirely perpendicular to b. We know the magnetic force now is going to change that entire vector, and it will be the component that ends up, we said before, ends up kind of starting to loop around magnetic field lines. We should be able to kind of justify that to ourselves and argue that if we were to do this super carefully in the calculus limit, we would indeed get circles. So again, we know that, and I think I already said this above, but since V is perpendicular, well, it doesn't really matter. Since the force is perpendicular to V, that implies then the acceleration that the charge experiences is perpendicular to V. So again, V can't change in magnitude, but it can change in direction. So then that means the magnitude of V in this case is just always going to be V0. Always. And I guess, yes, since there is no parallel component to B, I can talk about the entire velocity vector, not just the part that is perpendicular to B, since the entire thing is perpendicular to B. So you can imagine then, let's practice the right-hand rule. The charge enters, and now it's at this point here, where it's just entered the region where there's a magnetic field, and so a force has clicked on that point. What direction is the force? Try it out for yourself before I give the answer. So if we assume it's a positive charge, again, V cross B, my hand points in the direction initially with V, and then the only way I can have my fingers curl out of the page without breaking my knuckles is if I have my hand kind of open facing myself. And so then it looks like the force points to the right in this case. So then that's the magnetic force. Similarly, the acceleration it experiences. So in that case then, the velocity is going up. It feels a force point to the right. That's going to want to make the velocity vector veer to the right. You can imagine, and I'll do this kind of in bulk. Of course, in reality, we would do this more carefully in calculus. Okay, it's going to then kind of start to veer that way, say, as a result. Then that new velocity vector is kind of pointing this way. V cross B. Again, convince yourself then that the force points in that direction. So as a result, it's going to then point kind of like this. V cross B, convince yourself, points in that direction. Then it might end up pointing like this. V cross B, points in that direction. And I think you see what's happening here. And it points like this. V cross B, that. not quite leave myself. No, I did, just barely. Enough room. And it kind of ends up looking like that. V cross B, I guess, yeah, point still downward there. And as a result, let's see, did I do this symmetrically? I guess I did. And then it would end up kind of coming out that way as a result. So you can see that what's happening here is that, really this is kind of more just to keep with the symmetry, ends up being closer to being horizontal. So what's happening is that the velocity vector is kind of being pulled around, and then, in this case, we had the magnetic field turned off after it completed half a circle. What's happening is that it's tracing out a circle. If we were to do this with very, very small time increments, then the velocity vector would trace out a circle. So we get something that comes in, and it would start to do something like this, and then it would come back out. Where, in every instance, the force would be perpendicular to the velocity. Now we know what happens, what kind of motion that is. We know how to describe that motion from Physics 1. Right? If A looks like it's center seeking, the acceleration is always pointing towards the center of the circle. There is no A parallel component, and that is parallel to V. So the thing can't speed up or slow down, it can only change direction. This then is, of course, uniform circular motion. So, uniform circular motion. All right. Now, one acceleration, that seems out of the blue with idea to memorize. But again, it comes up in a lot of different contexts. It's worth knowing when you work out the math. It's easy to work out in polar coordinates. I don't know how much of that you did in Physics 1, so I don't want to confuse the matter too much. So, but, the simple F equals ma problem, right, F equals ma. And again, if I did this in polar coordinates, which means that my directions aren't x, y, and z, but in and out of the circle, radially towards or away from the center of the circle, and then tangential to the circle. The force is pointing radially inward. So as a result, the acceleration is pointing radially inward. And then we have that the magnitude of the acceleration in uniform circular motion is just v squared over r. And it points towards the center of the circle. So, as a result, you can write down that the force in this case, I can even write it in polar coordinates if I want to. Why not? That the force, if we use little r as the radially inward, then the force then looks like it's going to be, let's see, what would it be? I guess it would be negative q v naught times the magnitude of the magnetic field. And that all is in the radial direction, so towards or away the center. So since it's negative, that means it's towards the center of the circle. And then that equals, of course, the mass times the acceleration in the radial direction, which we write as v squared over r in the radial direction, negative v squared over r. And so, in that case then, all this says is that Q V naught times B equals M V naught squared divided by R. And you can solve and find that the radius of this circular motion is just M V naught over Q B. The radius. Sometimes I think it's called the synchrotron radius. Or cyclotron radius, rather, sorry. Cyclotron radius. That's what I highlight. And when you're in a uniform magnetic field, and maybe I'll even put B naught, right, really to remind myself that this is a uniform magnetic field. And when I'm in a uniform magnetic field, the velocity, again, technically the velocity component that was initially perpendicular to B, but in this case, that's the entire velocity vector, just gets twisted around in a circle with radius mv naught given by qb. All right, so a couple things to point out, that if I write the radius as v naught over b naught times m over q, we can ask ourselves kind of what are the dependencies on this. So the dependencies seem to be that if you have a larger v naught, right? Say you increase v naught, what does that mean? That means a bigger circle. That kind of makes sense. I have more inertia, or momentum, really I should just say momentum. I have more momentum in a particular direction, so the force has to do has, I don't want to say work harder, but it has to exert its its efforts to change the direction, and as a result it traces out a bigger circle instead. Similarly, if you have a stronger magnetic field, it's in the denominator, you get a smaller circle. And then this other quantity m over q is called the mass to charge ratio. This mass to charge ratio experimentally it plays a very important role, because often when you're designing experiments involving magnetic fields, the particle that you're accelerating around will have some mass and will have some particular amount of charge, right? If I'm trying to accelerate a proton compared to, say, an oxygen nucleus, those have different masses and different charges. Often it's the ratio of these two, the mass to the charge, that matters. Like in this case, in terms of what particles I'm trying to accelerate or move around in a circle, depends on my mass to charge ratio as a result. All right, I'm out of room on this page, so. Let me give another example of this that I think is important to talk about. Well, let me give a cutesy little example, which are auroras, and then actually go and talk about how synchrotrons and cyclotrons work, given the results we just had. Auroras, this will be, we'll do a qualitative one, and the synchrotron and cyclotron will be quantitative. So for auroras, the idea is that you've heard of the aurora borealis. If you come from the southern hemisphere, you've heard of the aurora australis. The idea is that our sun, while it emits lots of radiation, of course, it also emits a lot of particles. There are a constant slew of mostly protons and electrons flying off the surface of the sun that we call the solar wind. So the sun, exerts a solar wind of charged particles and something like several like tons of pounds per second. Of course, the sun is enormous, so it's never losing any considerable amount of mass. These charged particles, of course, some of them are in the direction towards Earth. So drawn not to scale at all. All right, if this is Earth, some of those charged particles make their way towards Earth. Sometimes the sun has more energetic events like solar explosions that go on the surface, where you might get prominences or flares. Those release a lot of energy, a lot of particles. If those happen and happen to be pointing towards Earth, there's considerable concern that all that could fry our electronics. We should be thankful, though, that the Earth, because of something we don't actually quite fully understand yet, but we believe has something to do with some sort of, hot, molten, mostly iron, rotating ball in the center, in the core of the Earth. Essentially, it is a bunch of rotating charges, right? If you think of, hot iron, and lots of charges flying around. If I rotate them all in circles, you have a lot of moving charges. We will talk about next lecture. That actually is creating a magnetic field. So the Earth ends up essentially having a giant bar magnet inside of it. Now its exact shape is not a perfect bar, but where close to the geographic North Pole, that's kind of where one end of the magnet is, and close to the geographic South Pole ends up being where the other magnet is. They're actually somewhat offset from one another, which actually, quick aside, actually is why when you use GPS, right, that can point you towards the geographic north, where if I hold a magnetic compass, that's the worst responding to the magnetic field of the Earth, that is pointing me towards the magnetic north on the Earth. They are two different locations. They are not identical locations. One is the geographic north is just based on the rotation of the Earth, where the magnetic north is kind of where the magnetic field kind of originates from, if you want to think of it that way. But in your smartphones, actually, right, your smartphones have both an accelerometer or compass and and uses GPS. So if you go into your settings for your compass, usually it will have an option that says use true north on or off, right? Whether you're talking about geographic north or magnetic pole north. Us in the northern hemisphere, or in the United States, it's not introducing any significant error. But again, if you're in the upper, above the Arctic Circle, for example. Anyway, so we have this magnetic field that is creating a shield around the Earth, such that what happens is that when one of these charged particles makes their way towards Earth, once it hits the region where the magnetic field is, it starts to undergo helical motion. And then it kind of does that and follows the magnetic field, which kind of gets channeled towards the North and the South Pole. So then another charged particle here kind of gets channeled and follows the magnetic field that way. So as a result, these charged particles get channeled along field lines and eventually do crash into our atmosphere near the North and the South Pole, which then creates the northern lights, for example, in the northern hemisphere. What's happening is those charged particles crash into our atmosphere. It then runs into the diatomic nitrogens and oxygens and whatnot, and that excites the electrons in those molecules and can cause them to glow. So those colors you see is just our atmosphere glowing from these collisions. It's a pretty effect, as long as that's it, right? Too many charged particles from the sun, and right, then bad things can happen. All right, let me talk now about cyclotrons. So I guess in this case where you get auroras. So for the cyclotron, the way a cyclotron works is you have this kind of circular device, and there's this very thin region. See how thin I can make this. This very thin region down here. Actually, probably much thinner than that, but that's okay. And then, and this thin region essentially is a little gap that is hooked up to an oscillating potential. I'll draw a little squiggle there. And then these regions, they're called Ds, because it kind of looks like a forward and backwards letter D. If you don't see it here, the letter D and then a backwards letter D are pervaded with a uniform magnetic field. So we have a uniform B field. In this case, it looks like I drew it out of the page. And then in this gap holds a constant potential difference. So there's an electric field that's in that little gap that points either left or right. And the idea is the following. The idea is that if you want to accelerate a particle up to high speeds, you can take a particle, maybe we'll just work through it. Let's suppose you start a charge that has charge Q, and again, let's stick with positive to make our life simple, and it also has mass M. So let's maybe it's a proton. Then the charge would be plus E, mass would be mass of the proton. And you launch it in the center. And suppose with let's say you release it from rest, right? We launch it with a velocity that's essentially 0 in the center. It then will accelerate through the gap. So if I have it near the center, maybe it starts here, big circle, and it accelerates through the gap. And again, the gap is very small, so it just essentially just gives it a kick. It accelerates through the gap. So you start with some charge V0. It accelerates by the electric field through the gap. Thought I was out of room. Through the gap. And so then its kinetic energy does change. The electric field can change your energy. The change in kinetic energy through the gap is of course equal to the charge times delta V from way back in the day. So in this case, if it starts with kinetic energy close to 0, then 1/2 mv final, which I'll call V1 in this case. Where we start at V0, let's call this V0. And then it accelerates by E, so then its new velocity, really the change in kinetic energy, I'll just write out explicitly, which in this case, there is no initial kinetic energy, equals Q delta V. And the whole goal is that this oscillator machine at the bottom holds a constant potential. So in that case, then it looks like V1 is just the square root of 2Q delta V divided by M. Note that the ratio M over Q appears again, though in this case it's flipped, Q over M. So now it has a little boost of speed. it then enters the magnetic field region on the right. It enters the B field on the right. It feels a magnetic force. Again, if V is going to the left, B is out of the page. Seems like it's going to feel a force that initially points downward, but we know from on the previous page, it's going to complete a little semicircle. It's going to complete half a circle. Right, so maybe that does, but right, follows a semicircle with radius. In this case, the initial radius it has looks like it's mass times its velocity, which was v1 in this case, divided by q times the magnetic field. So, since v is very small in this case, right, it's only gotten a little boost so far, it completes a little half circle. We could ask now how long it takes to do that. So it completes a semicircle with radius r1 in a time delta t. Now, I mean, this is just geometry. It completes half a circle, and it's always doing it at the same velocity. So it completes half a circle, so it's not 2 pi r, but it's just pi times r, divided by the velocity it has, which was just v1. And so then it looks like this is m, the v's cancel, divided by qb, lost a pi m over qb. Note that it does not depend on the velocity. Note that it depends on 4 quantities that are never changing, right? The mass of the particle is never changing, this magnetic field is always a constant, and the charge is always a constant. So note that this does not depend on v. That's going to be key in a second. So the particle is accelerated, it completes a little half circle, and then it's back to the place where the electric field is. Now, if the electric field doesn't change, it's then going to end up slowing down as it goes back through the electric field in the wrong direction. So the point of this oscillator here is that it reverses the E field direction in some regular way, at some frequency. So if the oscillator device, which you might just get by some sort of alternating current device, flips the direction of E, then the particle accelerates again. So, electric field goes this way, it starts here, gets a boost, does half a circle, but by the time it gets back, the oscillator device has flipped the electric field, so then it gets a boost again. Then you might imagine what's going to happen. It's going to do half a circle, it's another boost. Half a circle, does another boost. Half a circle, and then we can just accelerate. So essentially that electric field is what accelerates the thing over and over and over again, just by giving it tiny kicks every time. But you do it 10,000 times, you can really speed up a particle. Let's get rid of, I might not do all of that, also for sake of time. So accelerates the particle again. So then the change in kinetic energy is again Q delta V. And so as a result, you could ask then that change in kinetic energy, which is going to now be 1/2 mv2 squared minus 1/2 mv1 squared equals Q delta V. You can then solve for and find that v2 equals the square root of v1 squared plus this quantity 2q delta V over m when you solve for the velocity v2. But v1 is just the square root of 2qv over m, delta v over m. So it turns out that this just ends up being the square root of 2 times 2q delta v over m. So then it does a new semicircle, because now it's on the left side. I can't see the picture anymore. Now it's kind of on this the left side of the D, or the left D, left side of the synchrotron. But now it's doing it with a new radius, because the radius does depend on the velocity. The radius r2 now is mv2 over qb. So it's a slightly bigger radius, but then does a semicircle, accelerates, does a slightly bigger semicircle, accelerates, does a slightly bigger semicircle. So the overall path, right, then repeat as many times as you can. So the overall path if I draw my like that, the overall path is it might start here and then it just does something that looks like this. And then eventually it gets to the end where there's some detector that will, through probably other magnets, redirect the path, and the particle, and the particle can shoot outward instead of continuing on the circle. And again, this is what essentially particle accelerators can do. You can just spin things up and get them to very, very high speeds. So if they start getting really, really fast, then you have to switch over to synchrotrons instead of cyclotrons. Let's finish this idea of cyclotrons. So essentially, again, if you have you can ask, how much time. So one full loop takes time. We can give it approximately by what we had above, and say it's 2 delta t. Or, and write that as, because again, you might think, well, half the circle is at one velocity, but then the other half of the circle is at a different velocity. Remember that delta t didn't depend on the velocity. So in this case, it's just 2 pi m over qb. Now you might be saying, what about the time it's in the gap? Well, that's why I kept saying that the gap is usually very, 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 very small, right? It's a tiny little boost. It's essentially just a little perturbation kick. So we're considering that negligible overall time. So this then is the period, right? Capital T. The period of motion, And going back to the helical paths, right? It's the same sort of idea. The amount of time it takes to do one loop. This defines the cyclotron frequency. Oops, Cyclotron frequency. Which then frequency is just 1 over period. So that's just the inverse of this. QB over 2 pi m. My equations get mixed up. Or sometimes angular frequencies are useful if you want to talk about, because cyclotron frequency is kind of, you can think of it as cycles per second or whatever time unit you're using. Angular frequency, you might want to talk about number, if it's completing a circle, that's 2 pi radians. So you might want to think of it as how many radians per second. So then there's 2 pi radians per cycle. So then the relationship is then just 2 pi f is omega. So then the cyclotron frequency then is just the 2 pi's cancel, QB over M in this case, which has units of radians per second, or whatever you use. This is why this is important, is because that oscillator needs to know when it needs, how frequently it needs to flip the electric field. So why this is helpful is that, since this frequency, since the oscillator frequency is independent of velocity, that means if it just flips the electric field at some normal rate, say one time a second, or 1 cycle per second, so that would be 2 flips, in the electric field, the cyclotron can work, right? Because the particle is always getting back to this region where there's an electric field in the same amount of time, no matter how fast or how slow it's moving, which is kind of cool. Right? The reasoning, because as it gets faster, it's completing bigger circles, and those effects are canceling out in this case. So we can use this to set the magnetic field. So if your device has an oscillation frequency we'll say f-osc. Right, if it has an oscillation frequency, right? If you've built an electronic device that's going to flip the electric field twice every second, or every microsecond, or every 5 seconds, that'd be very inefficient synchrotron. But then the requirement is that you want, for the cyclotron to work, you want to set f equal to this oscillation frequency. Then that essentially is a way where you can determine the strength of the magnetic field that you need in order to accomplish that. Then you can see, if we go back to the velocity, when we worked out for after it passes through the electric field twice, its final kinetic energy is this. You can imagine that this can generalize, that this 2 becomes a 3, a 4, a 5, etc. So after n oscillations, after n complete oscillations, or maybe I'll just even say n orbits, right, or oscillations, which again, you underwent 2n boosts. And your velocity in that case, after 2n boosts, is then just square root of 2n times 2q delta v over m, where this is capital V, potential V. So what really happens is that you can have a very modest, you can even have the delta V, the potential in that region, where the gap is very small, and you don't even need to have, it doesn't really matter if the delta V is very big, right? You could just set this on like 100 volts. But again, if you do this 10,000 times, 10,000 boosts, you can really start to ramp things up. And that's kind of what you do. Now, just quickly, I'll just comment that this does have its limitations. Of course, there's a constructural limitation where if you want, the bigger the final velocity you want, the bigger the device you need. But then relativity starts to come into play too. So just a quick aside on synchrotrons. That once your kinetic energies of particles which again are tiny little masses like protons and whatnot. Once your kinetic energies start to get on order of, say, like 500 giga electron volts, which is again is the kind of unit of energy we use for protons and whatnot. Just for example, when the kinetic energies are comparable to that, for a proton in a modest electromagnet that maybe has a magnetic field of 1.5 teslas, the radius, the final radius, is something on order of 1.5 kilometers. Sorry, more like 1.1. So again, constructually, right, this is becoming somewhat demanding. Also, relativity starts to kick in, right? So then you also have special relativity effects. Where the velocities don't add quite as simply as what we've been talking about. When you start to get within, like, say, 10% the speed of light, beyond that, really you have to start adding velocities relativistically. In that case, it turns out, then the period does end up depending on velocity. So it turns period t into a function of velocity too. Which means that essentially then the particle gets out of sync with the oscillator. So particle motion is out of sync with the oscillator, the thing that's controlling the electric field in the middle. And so what you do is you upgrade to a synchrotron, which keeps you in sync. So in that case, then the device, it itself changes the oscillation frequency so that it does keep in track or in sync with the particle. So I guess synchrotrons fix this. That's all I'll say about synchrotrons. But these devices, cyclotrons and synchrotrons, have been incredibly important. The discovery of the nuclear structure of atoms, right? The fact that the nucleus is protons and neutrons was devised, as well as quarks, as well as the fact that protons and neutrons can be written as these things called quarks. All were done in these sorts of devices. You probably have heard of the CERN particle accelerator in near Geneva. The idea here, particularly this kind of blue line, right here, is the superparticle synchrotron, the SPS, which essentially just is a way to get protons up to nearly the speed of light. And there are other devices that, through mostly magnetic fields, can channel things into this bigger loop. It's 27 kilometers, I believe, in radius, something like that. Maybe that's circumference. But you can see it's built underground, underneath, whatever's going on the surface. And through these devices, right, we can throw particles at each other at essentially the speed of light. I think, here's kind of the overall device, where you kind of always see it as kind of a loop, and then there's a smaller loop here. The smaller loop, right, is the smooth super proton synchrotron. Kind of fun. So all those things about the bosons and Higgs boson and all that stuff uses a lot of these devices. So these things are worth talking about. All right, how are we on time? All right, we're over time. Let's see. What of this can I cut? All right, I'll nix the Hall effect. let's see, I can move this stuff to the next lecture, but I do want to, because I want us to start thinking about things, so another important effect of magnetic fields is I want to kind of sketch out the force on a wire with current. So, and this is very simple. It's a very simple extension of charges. So suppose I have a wire, and there's some current in it that's going in that direction. Then I have some magnetic field that's in the area, which I'll assume it's uniform over the entire wire, or this wire segment. So there's some segment of wire I'm going to say has length L. And it's a straight wire. All right, so we have straight wire. Right, why does it have to be straight? Well, think of the right-hand rule. The current is essentially telling you the velocity of the charges. And since the velocity plays a role with the force, we use a straight wire segment with length L in a uniform magnetic field. Remember, what's actually going on inside the wire, right? There are charge carriers that are drifting around, right? They're more or less, they're moving in random directions and colliding with each other a lot, but there is kind of a very general slow drift of the charge carriers through the wire. So if I points that way, then on average, the charge carriers have an overall drift velocity I'll say v sub d that points that way as well. So that's important because then that's the velocity we use in evaluating the force. So, and then we can just write this out with a little bit of calculus, and it turns out to not be too bad. So, if I look at this wire and I break it up into a bunch of tiny pieces, that tiny piece has some amount of charge dq within it over some tiny amount of length dl. Excuse me. And of course, they're connected to one another. So then let's evaluate the total force on the wire. So, perfect, because I'm out of room. So if we start with the force for a given charge, right, which is Q, V cross B, then we can say for that tiny amount of charge in a segment of wire, that tiny little segment of wire has a force, that's given by dq, then it has some drift velocity cross B. Actually, I don't even need the subscript for drift anymore. All right, it has some little velocity that's going in the same direction as the current. I am going to use our definition of current first, is I'm going to, noting that since current is dq dt, I'm going to first write this as I, then I have v dt cross B. I then identify v times delta t, as we did earlier, is some little length d little l, which is a vector, cross B. So again, off to the side, just right underneath. So dl points in the same direction as the drift velocity, or the same direction as the current. That is current, despite what it looks like. And then we have a bunch of constants, right? The magnetic field's a constant. We're saying the current reaches some sort of steady state. This actually then becomes a pretty easy integral. So then the total force on the line segment is the integral over the segment of I dl cross B. But since I is a constant, it can come out of the integral, and B is the cross product with B is a constant. But since order matters, I'm not going to pull it out to the left, so I might write it as just I, then parenthesis, this integral, and then whatever the answer to that integral is, cross it with this constant magnetic field. So then it looks like I'm just adding up all the small pieces of length, so then this just becomes I, and I'll use capital L cross B. So then, so then the force is then just I, L cross B, where L points in the direction of I, and the magnitude of L is just the length of the segment. So if it has a length total of capital L, you have a magnetic field, you can calculate the force using the right-hand rule. Let me just do one example and then we'll be done. All right, so I have some line of current here, and let's suppose that I have B pointing into the page. There's some current that's moving in that direction. And the entire length, this entire thing is length L. Then the force is, I point my fingers in the direction of the current. Then it seems like if I have to curl my fingers into the page by the right-hand rule, looks like the force on this wire points upward as a result. And again, notice it's the same thing you would get if I said there's a charge, a positive charge moving to the right. By convention, the conventional current is that it's positive charges flying around, and when you calculate the force, it seems that the wire is being pushed upward. There is something called the Hall effect, which maybe I'll do next time I work into our problems that we work on in class, where you might think, if you think about this, if we assume the current is a bunch of positive charges, then it seems like if I were to make a magnetic field, the wire should feel force pushing upward. If the current was actually negative charges moving in the opposite direction, would you expect the same result? Well, if we think about it, negative charges, but then I have to flip it because it's negative charge, you actually do get the same force that also points up. Okay, well that's at least good, right? Because whether it's conventional current or actual current, right, we should get the same physical result in terms of forces. But then there's something called the Hall effect, where actually within the wire or within some sort of conductor, we can see that whether it's positive or negatives, you do get these subtle little differences. So anyway, that's just a detail for fun. All right, let's end it here.